Okay, welcome everyone to the third lecture. Okay. So before we start, any question about last week? No? Because you were busy on the weekend, I guess, no? Reviewing the material, playing with the simulator, etc. Okay. So for today we are going to just go through some things that we didn't talk about or I forgot to talk about last week, just to complement those topics. And then we're going to go on the more focusing on the uncertainty and how do we quantify first uncertainty in the field planning process. We are going to go to one particular example just to show which kind of tools do we use. And then we're going to go to one particular example that is to estimate reserves, like a very rough or very initial, when you are just in the appraisal phase or you are in the field, how do we call it, business identification phase. How do we estimate and report reserves? And how do we know if we want to go forward or we just want to relinquish? So before that, that's the menu for today, right? Before that, some people were asking if I had a tentative date for the exercise, and the first set will probably be for the end of last week. Okay, so that's not 100% sure, but tentative date for first set of exercises, the end of next week. Okay. And the exercises usually have between 3 and 4 questions. Okay, each one of them is almost like a small, like some certain number of tasks. But that's if we do it sooner, might be, but I think more realistically will be by the end of next week. Right? So let's, before, just to wake you up, let's first see that this is recording. Okay. Have you tried Kahoot before? Yes. Kahoot, yes? You know what Kahoot is? So we're going to make a small quiz. Today there are no prizes, so don't feel obliged. You just win for the fun of it. But maybe in the future we will have some prizes. Okay. So let's see. So you have to go to kahoot.it. Classic. Okay. And then you have to put this pin. You can do it from the cell phone, okay? Just to make sure that we're checking you remember what we discussed. Don't put non-adequate names. just six questions. PDO stands for put. And what is the generic name that we discussed? Plan for Field Development. Okay, PFD. Last class. Okay, a kick on the first. Okay, what follows in the field development process after the process planning? Okay, what are roughly the steps? You have a business, what they call business identification phase, okay, which comprises of pre-exploration and exploration. What else do you have there? Then you have the project planning. After you say yes, we think this is commercially, it has commercial potential, we are going to go forward. So there you have the project planning. Then you have project execution, where you have the detail engineering, building, commissioning, installation in place, etc. of the equipment. Then you have operations, okay, and then at the end you have the decommissioning. The appraisal is part of after you have the exploration, you have made a discovery that you are appraising to see, to assess better how many reserves you have. Okay, so we have still a clear winner. That is typically done during operations. Okay, debottlenecking is that you have a limited capacity, for example, of gas processing, of water processing, and you have reached it. Okay, and you want to that's being that you are in the bottleneck. Okay, you have bottlenecked facilities. So debottlenecking, you try to find ways, either reducing the water production, either having additional processing units that will help you to produce more. The goal is to increase the production of the primary phase, okay, oil or gas. Some tasks that are done during decommissioning are plugging and abandonment of wells. Okay, we have the cut of the conductor of the casing, some meters below the seabed. We have the removal of the offshore structure, removal of the processing facilities. What else did we have? We have also this recycling, recovery of mainly steel material, and recycling of equipment, especially gas turbines, some separators, some processing equipment. We can use some other place. And if we have connectors, subsea, and we have templates, also removing these templates, removing the Christmas trees, and burying or removing the subsea pipelines. Okay. Mutesen must hurry up. Okay. According to DAKE, which is the one that explains about onshore and offshore, how do you plan or when do you plan the pressure maintenance of the vessel? Gas injection is usually planned from the beginning. That's a very big difference with onshore. Onshore, it can wait after you have been producing for some time, assess the extent, assess if there is communication, where do you plan to inject, and then have a proper injection plan. Offshore, we don't have that luxury. We just plan, make an assumption, and then it could be right, it could be wrong, or has to be corrected. Okay? Wow, what happened here? Okay, which one of the following statements is false? Let's see which ones are true. If you remember, production A was plateau production, okay, and production mode B was decline. That you're operating at constant choke opening, and the other one is that you're constantly changing the choke opening to have a fixed production. Okay, so field production mode A is almost always followed by mode B, okay, because there comes a point where you have no more control. You have open choke, and then you start to decline. That's true. A field could be producing using mode B and then mode A. And that also could be true if you still have choke opening left, right? If you have the choke, for example, half position, and you have been declining your whole field life, but then you start to open it, you can still get a constant flow rate, right? So that's also true. That we already spoke, it's obvious, it's the wellhead is open gradually. And production mode B, remember we have a peak that we're going to have only for the first millisecond of the first hour of the first day of production, and then it will start to decline. So we will use that capacity only for that instant. So we don't usually use it for standalone projects. Okay. Now we have Mutesen back on the competition. Okay. As a rule of thumb, how much is the annual offtake of an oil field in the North Sea? Stands for total recoverable reserves, okay, which is the ultimate recovery factor times the initial oil or gas in place. For gas, 3%, between 5 and 3%. Okay. Rule of thumb. Okay, we will see today. I'm going to talk a bit about the plateau. Okay, so 19.1, and I'm not sure if I can get. Not the full ranking, okay? Not sure if I succeed at waking you up, but at least we do something a bit different. Okay? Yes, some things that were, so I'm going to talk now about things that were missing last class, okay? And so for gas, we usually have to consider for gas development using existing, remember that the gas we have to use either LNG or we have to use an existing pipeline distribution network, okay? So we usually have to pay, this pipeline belongs to someone else. Okay, doesn't belong usually to the project. So we have to pay for gas development using gas, using a gas distribution network. A tariff that is certain amount or percentage of the production, depending on how much you are transporting on the pipe, has to be paid. okay, to someone, to in Norway it's organization called Gassco. A tariff must be paid. Okay, in Norway is Gassco. Okay. And that's after I have processed my gas, that it already is in a, they have some requirements for this gas. Okay, they must have almost no liquid, must have a certain dew point, must have certain content of CO2, must have certain content of just very similar to the gas specs. Okay, to be allowed to be transported in this system. So I think I have a picture of. So that's a Norwegian okay, gas transportation system, okay, which is managed by Gasco. And if you have a finding that you, for example, are someplace here and you want to use this pipeline, then you have to take that into account. Okay, just using the transportation space in the line to send it further to the consumers in the UK, in Europe, etc. Okay. Yeah, sometimes like you will see, I will post a video maybe next week. It was a guest lecture. He came in 2013 from Statoil, and he's talking about Osta Anstein, maybe you correct my pronunciation, a new field that is being developed more or less here. Okay, and they analyzed the possibility to tie it here to this part of the gas transportation system, but Gasco told them that the capacity was more or less at maximum, that that pipe could not take any more gas production. So they decided to build their own pipeline that goes all the way, I think, to Nyhamna. Okay, but you can see more about this issue in just to make you aware of it. That you can see more on the video that I will put on its learning. Okay. Okay, and in usually another comment about gas is in gas contracts. You usually have a what is called a daily contract quantity, a DCQ. That's how much the customer wants and how much you are committed to supply. And it might be an average, it might change a bit in time, it might change a bit monthly, but that's the average of the in that period of time. And then you have also a swing factor that is a multiplier to DCQ. Okay, and that means how much additional or extra capacity I have to have above the DCQ. Okay, it can be 1.2, 1.3, 1.4. How much in a particular instant, if the customer wants, I'm able to increase production. Okay, and also there is a penalty. Usually there is a penalty clause. And that is how much the producer has to pay if doesn't deliver DCQ. Okay, and that's important when we have some problems in the field. You're not able to produce, or you have some days that you have to execute maintenance, you have to shut down operations for some reason, that's something that you have to pay the customer because you failed to deliver what was promised. Okay, just things to consider. Then on the production, about something's missing about the production profile. Yeah, should I go up? Okay. This decline, it's mode B, right? And it can be, like I told you, if you visualize it in this very simple analog, that is a constant choke. Okay? But I can also constant choke opening, but I can change the choke opening for some reason. Okay, some change can happen in the system, like for example, I can produce more, and then I will start declining again, or I will produce less. Okay, and it will continue with the same decline. Okay, so it's not forcefully that we're going to have all the time a uniform decline. That depends on the characteristics of my production system. Okay, I'm talking about choke, but can be really everything. It can be like the well bores collapse for some reason, and then I start producing less. The wells are starting to. All of this, if you see our mechanical analog, let's go to last lecture. Really, I'm saying that the thing that I can control, that I can use to control my production, to regulate my production, is the choke. Okay, but really, any of these restrictions can change in time, for any mechanical reason. If you see that this is the formation, you might have collapse of the formation in the wellbore. Okay, if you have the tubing, you might have formation of scale. You have some accumulation in the wall of minerals that are obstructing the if you have the pipeline, you might have there is too much liquid accumulated. Okay, and all of these things, they cause some deviation from the decline that you had of the system at constant choke. Or some other cases is just that you changed the choke and then you have a jump up or down and then it continues decline. Okay, and some examples, I just pulled some that is from an article. And this is the reference if you want to read it in more detail. So let's put it here. Okay, liquid loading is when we have accumulation of the well doesn't have enough energy to take the liquid out of the wellbore. Okay, to take the liquid out of the tubing. We can have wax accumulation. Okay, and for example, this you see they try to have the Prudhoe Bay. I think that's in Alaska. I think. Yes, and then you can almost feel an exponential to this decline. Okay, very very smooth. And this Thistle, I think it's a UK offshore field. Yes. And but then you have some others that have more of a jumpy up and down. Okay, and these are because you have changes in the production system. Might be that you're doing it unintentionally by changing choke, by changing some other equipment. Remember that choke might not be the only component that I can change. Okay, I can have pumps, for example, and pumps they do the opposite effect. They don't create a pressure drop, but they create a pressure increase, so I can produce more. We're going to talk a bit more about that later. And also here. But in average, the decline, you can fit it more or less to, some people say there are different declines, but usually people use exponential, okay? And we will, again, talk about that when we talk about production potential, and we will see why we get exponential, but there are some cases that we could get something different, okay? It depends really on the decline of pressure with production, the material balance. Yes. Okay, then was one or two more things that please know that there is a very close relationship between plateau length, okay, and plateau height, okay. Let's skip. Okay. Usually is if I have a higher plateau, let's call it QP, then I have a shorter length. Okay. And if you think, we will see later why is that, but if you think about that, I all the time have to recover the same. Okay, you say all of these three is the same development, the same reservoir, so I should recover the same amount of material. Okay, the same, we can call it NPU in the case of oil. Okay, so it's ultimate cumulative production. Okay, that is the integral from time 0 to time t end. Okay, the t end might be different, of Q of the field dt. Okay, t end is this in this case. Okay, so the area under that integral is the area under the curve. Okay, this area in this case, and I'm not going to put the others because they're going to get messy. Okay, but if the area has to be the same, then I can have very high but very short, and to be equivalent I can make it very small but then longer. Okay, so you have to have all the time an equivalence, a correspondence between these two. Okay, so you will say, okay, how do I decide then the plateau? Okay, if you're with gas, usually that comes by the contract. Okay, that depends mostly on the customer. Okay, but we do an economical analysis. Okay, and then we choose one plateau that will maximize my NPV, my net present value. Maximize NPV. Okay. If we go higher, then in this case capex, okay, we will talk about economy on Thursday, but capex, capital expenditures, facilities, platform, equipment, etc., is going to be very high. Okay, but the good part is that I'm going to have early cash flow. Okay, I'm going to recover most of it very quickly, but the capex is going to be very expensive. In this case, capex is lower, but then I'm going to have a late cash flow. Okay, if you see, it's much less, but I recover in longer period of time. So usually it's a balance between these two, and that's done with an economical analysis. We're going to do some one exercise on that later. Okay, but just to have an idea. For you, if you can think now about it, the area has to be the same, so I can have very big plateau, short, but very long, but shorter. Okay, that clear? Yes. Okay, and really here, one thing that you have to take into account, its height. Okay, is dictated by physics. Okay, or engineering. Sometimes my production system cannot produce more than that. It's a physical limitation. If I increase that rate, for example, my formation will collapse. I will start to produce too much sand. I will have erosion, and I will destroy my. So here, let's list that. So we have, if Q is higher, then I might produce excessive sand. Then erosion, damage, okay, for a given production system. But it's also dictated, as I told you, by the economics. Okay, I usually try to select the plateau length depending on my NPV calculations. Okay, while length is dictated just by physics. Okay, I cannot say it's more economical to produce 3 more years, and then I force my production system to produce for 3 more years. So I think I make this mistake all the time, that I put things in the header. Okay, but length is dictated by physics. I can do some modification to the production system to make it produce longer. Okay, but really it's a main constraint given by physics. Physics is going to tell me, okay, if you choose this value, you're going to end up here. If you choose this value, you're going to end up here, etc. Okay. Okay, just before we go to the break, another thing that is how to compute production profiles. Okay, because what is important, production profiles, let's put it here in red. Production is the only is the only source of revenue. So it's a number, or this profile that we have is crucial for all my process to take my decisions, because it's the only source of revenue. All the rest is expenditures. So I want to have a really good estimate of how my production will look like. Okay. And if you see a bit about our tank, let's take our tank example. Not from here, but we can take it from Okay. It's important that I will have a relationship between PR as a function of, let's call it NP, okay, cumulative production. You already saw what NP is, right? We can say NP is for oil, GP is for gas, or we can call it QP, that is generic, okay? If we want to do a generic discussion where Q can be either oil or gas, yes? But this, I can try to put it as a function of NP, but then I want something that gives Q of the field has a function of PR, of PS, and of the characteristics of all of these restrictions, okay? Okay, because just with this equation, I don't have much. I just say, I know how much I'm going to decline, and I might have a minimum reservoir pressure, but I'm not sure how much I can produce at each reservoir pressure. But with this other equation, so this is what we call a static reservoir equation, okay, or also material balance. You maybe heard of it in the course of Whitson, Professor Whitson, yeah, I guess. Some of you are taking that course just now, but maybe you have it from before, from your education, okay? Just a relationship between pressure and cumulative production. But while this one is a dynamic model, okay? And I need to have that to calculate rates, okay? I need to have that. So one option is, and we will see just after the break, we could use some options typically used are material balance plus an IPR equation. Okay. The IPR equation stands for, all of you know, IPR, inflow performance relationship. Yeah. And this is related to how much production will I get from the reservoir if I exert certain bottom hole pressure, okay, flowing bottom hole pressure. Yes? If you go on the, you have your well, okay, let's repeat the drawing, and you have your reservoir, then you have your tubing, okay. If you go here just in front of the formation, in front of the perforations, and you put certain value of pressure, if you put something very high, let's say that here you have PR. This is a well, okay? I hope that's clear. Let's do the rest. Okay. If I put here in front one value that is very close, so if I make now a plot, okay? Let's say Q versus PWF, okay? If I put a value very, very high that is close to reservoir pressure, I'm going to get almost no flow, very little flow. Okay. But as I start reducing this pressure, I will get more and more and more flow, right? So that's in short way, I'm very summarized an inflow performance relationship. Okay. So in this case, in this option, let's call it option 1, I'm neglecting all the rest, okay? All the things that go from this bottom, from the bottom hole all the way to the processing facilities, okay? So here it's neglects all downstream, all the system downstream the the well bottom hole. Okay. So that's one option, very simplified, but also I don't have at the early planning phases, I don't have the whole picture of the system. I don't know what is the depth of the well, probably. I don't know how many wells I'm going to use. I don't know if I'm going to use just a subsea system or if I'm going to use all the wells going to the platform. So really I don't have much information, so it's okay not to include all of that. But I have to use a proper bottom hole pressure value, a value that is realistic. It is important to use a PWF that is realistic and that allows the fluid to flow from bottom hole to separator. Okay. And that's a really big unknown. Okay. I can assume one value, but then I have to verify it somehow, and that in the design phase, when I include more things, I know more things about the system, I go and revisit and fix and update that PWF. Maybe the value I assumed originally was too low. Remember, if it's low, I will produce more, so it will be optimistic. Okay? If it's higher, it will produce less, but it might be pessimistic. Okay, so I have to use really a value that represents fairly enough, that will allow the fluid to flow from the bottom hole to the separator. Okay, let's take a break, 15 minutes, and we come back with some continuation of the discussion and starting on the answer. So, just to refresh, we compute production profiles, we need two things, a static and a dynamic model. Okay. One option that was used for many years and is still used in some onshore fields is to use material balance and an IPR equation. Okay. I gave you some, if because we are cutting the system in exactly here, we are not considering any of the rest because really we don't have much information about it. We have to use an appropriate flowing bottom hole pressure, and that's a bit tricky to find. You have to have enough pressure so you can flow all the rest of the production system. Okay, all the way to the separator. Well, that's really tricky. I can assume a value that is too high, that then I will have less production and it will be pessimistic. Or I can assume a value that is too low, and that will give me more production, and thus it will be optimistic, too optimistic. And another complexity is that it usually changes with time. If rate changes, then that required pressure will change. We will see later in flow equilibrium. So also that's another complexity. Usually we start doing some assumptions. As we have more and more details of our model, we try to incorporate them in the model. Okay. Another option, let's call it, I think, option 2, that is the most commonly used, especially in the North Sea, is to use reservoir simulator. Okay. The reservoir simulator, it doesn't have two separate dynamic and static, but both of these equations, one for mass conservation and then you have momentum conservation, okay, that is basically Darcy equation, are solved simultaneously in the same simulator. So you don't see actually these two modules, but all of them are in this one package. The problem, as you saw from Dake, is that you need enough information. This simple model needs very few input. Okay, you make average assumptions that you have an average volume, that the IPR is uniform, but to populate a reservoir model, you require much more information, and you require also some areal distribution of parameters. Okay. And if you don't have it, you have to make assumptions. And that's what he criticizes in this write-up, that it's better to have a simple model with less assumptions than to have a more complex model with more assumptions, okay, that you don't know. It will give you more robust results. But that's something that you have to cope, because you are kind of the fresh generation, and you have to cope and all the time be aware that the output of any simulator, of any model, depends on the input. So I have to look very closely at the input and see which things I'm sure of it, I'm 100% sure, and which things I'm just assuming. Okay, so big uncertainty. In the input, big uncertainty okay, so be careful. But that's the preferred, and in the reservoir simulator you provide, yeah, we will talk about it later, but you provide the same pressure, minimum pressure, and you compute the profiles. Yes, so let's drop a bit or freeze that discussion here, and we are going to talk about uncertainty, quantification, and management in the field planning process. Okay, and let's start first just by refreshing what are the main tasks of field planning. Are first, identify field development scenarios. We're going to use an FPSO, we're going to use a fixed platform, we're going to use another floater, for example. We're going to take it to shore, we're going to take it to with a tanker, we're going to use an LNG, we're going to use the gas transportation network. Okay, then you want to prepare details, or we say perform a pre-design of each scenario. Okay, then after you have proposed a scenario, you have to give enough details, then you have to study and analyze each scenario. Okay, then here you get the results or the performance of each scenario, and we will see what are exactly the performance indicators. Okay, but you get some results, and from these results you can compute some kind of efficiency or some kind of indicator that tells you, that will allow you to compare later. Okay, Then you want to rank the scenarios using a criteria. Okay, we'll talk about just now. And then you want to select the scenario, best case. Okay, you want to choose the best. And all of that, remember that is done if we put a timeline. Okay, project timeline. Initially I have, if we make it in a plot like this, initially this is the information. Okay, we have very limited information. Like I told you, this is very limited. Is just some exploration wells, some seismic, some geophysical data, and we have to make most of the decisions. So if we put now the decisions, so that's a typical plot that you will see many places. Okay, the decision, you can take many decisions at that point. But then with time, as you start production, you start expanding the amount of information you have. But then, ironically, the decisions that you can make are going to be reduced with time. Yes? So that's in time, you have less information, you can have the power to make many decisions, but as you progress, you will have every time less and less power to make changes, but you have more and more information. We want it to be the other way, right? We want to take the decisions with the best information, but that's how it is. Okay. So first, I'm going to talk just about the a kind of a block diagram of the asset, okay, of the field under study, of the asset under study. Okay. So first we have one big thing that are oil and gas reserves. Okay, we have one big box that are how much do we have in the subsurface. And that's what we are going to try to address today. I'm not sure if I will have time, but surely on Thursday we are going to cover it. And to calculate that, we need oil and gas. Okay, so this is G, this is N, and this is G. Okay, and here we have rock volume, parameters. Okay. Then we have rock and fluid characteristics. Okay, and we can put also here the, don't like to put it exactly here, but we can just take it from here, recovery factor. Rock volume, porosity, extension, structure, faults, all of these things are in here. Okay, so we can make just some examples. Don't want, you know, my diagrams, they start relatively okay considering my handwriting, but then I start putting things on top and it gets a bit messy. I'm not sure if that's your impression also, but that's my impression. Oh. Okay, so here we have porosity. Here we have um, structure, faults. Okay, all the things that we need to determine volumes. Okay, and also we say water oil contact, gas oil contact. Okay, extension of the reservoir. Then on rock and fluid characteristics, we have the saturation of oil, saturation of water. We can have the we have also the permeability. Okay. And on the recovery factor, that that really that really is calculated a bit afterwards. But here we have, for example, previous experience with similar fields and reservoirs. Okay. But we will see just now. So when we complete the diagram, so that's initially depending on the information you have. If you are in the pre-exploration, like we said, the business identification case, that's almost all you have. Okay, because remember we haven't done. It's really on the field planning that you start to paint the whole system. But initially in pre-exploration, that's what you have. Okay, so from here you just we can say here just a note that this is in the business identification phase, okay, just before planning. Okay, we are exactly here. Okay, and we don't have really more information to work on something more complex. So afterwards, just from here, we have another line that calculates the economical, we can call it economical value. Now, when we go on the project planning phase, then we take out, this is not so simple, right? The economical value depends on the field architecture that I'm going to use, on how much I'm going to spend in the facilities, what is going to be the production profile of the asset. But to get all of that, I need to start defining, I need to start doing exactly the tasks that I mentioned here. I want to identify field development scenarios, perform a pre-design study. So I have to break this, okay, take it away, and start putting all other elements in between. So let's see. So this information on the reservoir, I use it to compute production profiles. Okay, but not only that information, but also we need some information about the field architecture or field layout. I need also information about wells that so let's make it more organized. So field architecture, field layout that's one main big category, and under them we have wells, okay? We have offshore structures, We have also the subsea system. Okay. There is one thing that is missing. Of course, that's important. The facilities, the processing facilities. Okay. So that's the, like it says, like the layout, like the architecture, and the architecture is made, all of this very summarized, okay, very rough, but of wells, of the offshore structures, of the subsea system, and the processing facilities mainly. Okay. And I use that, especially depending on which degree of complexity, but I want to know how many wells I'm going to use to compute the production profiles. I want to use also how is the pressure drop. Am I planning to send all the production to shore, for example? I'm planning to send to a neighboring field to see how much is this PWF. Then we have another thing, which is the schedule, production schedule. Okay. I want to decide, here I have things like how much I will produce with time. Well, how much is going to be the production with time, if I have some preference. Okay. Maybe I can produce much more than that, but I will say I will operate in Plateau for this period and then I will decline. Or the customer wants me to produce in Plateau and then increase production for some years and then decline. Okay. So the schedule enters in there. And also before, that's the production and the production schedule. And also we have one more, which is the installation schedule. But this is not so important for the production. That's for later. Okay. Is there something else we are missing? Okay. Then with this input, we can compute. So you see, everything starts to appear. If I start, and generally this is in the business identification phase, but after I pass it and I go to the field design phase, I have to populate all of these boxes with some information, rough, detail, doesn't matter, but I have to populate all of these boxes. So here I use that information to calculate capex. Okay. Capital expenditures, how much am I going to expend? And also I'm going to use that, maybe we can pull it to the left, to see when in time that's going to happen. Okay, when am I planning to drill the wells? Where am I planning to order, to plan my offshore structure, subsea systems, etc. And also related to that, the production profiles and the layout, they influence in the calculation of the OPEX. Okay. What kind of processing facilities? What is the maximum rate that I will have? What is the size of the installation? How many people I'm going to need? How many trips I'm going to need offshore? What kind of maintenance I will require? Okay. Then from here, from the production profiles, I calculate the revenue. Okay. And the revenue is also calculated using a, we can call it here, well, just prices, hydrocarbon price. Okay. and that calculates also the profiles. You can use it to calculate the tariff that I told you about, how much I have to transport. Okay, and then all of these capex, all of these opex, this revenue, this tariff, they're going to be used to calculate cash flow. And something, we forgot something, right? We forgot the decommissioning part, right? So I think it's a bit tricky to the decommissioning. Costs. Okay, decommissioning cost, they depend on this. And this. Okay, until which day I'm going to produce, what kind of elements do I have in my system, and also the installation. When am I planning to start the decommissioning? Okay. And then finally, okay, I hope you didn't fall asleep. But then we have, after we have the cash flow and we have the decommissioning, we can calculate the NPV. Okay, and we have here also tax, the tax regime, and we calculate finally the NPV. So this is an overview, very simplified, okay, but like all the small elements that you have to define during a planning. All of these boxes have to be populated somehow, and the detail that you do it depends on which phase you are, how early or how late you are in the phase. Okay? But that's more or less what you have to populate. I think I have something else. Okay. So now comes but first see that we have, so in every box, or in every something else, just to comment that to work on that you need a multidisciplinary team. Okay, it's not only one person, but you need to have someone that is expert on the reservoir, some petrophysicist, some geological expert that can tell you about this part, some PVT expert. Okay. Then you want to have also one expert in reservoir simulation to compute the production profiles. You want to have an offshore expert. You need to have a drilling engineer. You need to have an economist that will make the calculations on OPEX, cash flow, and also tax. Okay, but you need to have a multidisciplinary team that they are communicating, because the outcome of them depends on the input of someone else. So they have to be communicating constantly. Okay. Do you prefer that I make those notes, or are you going to listen later to the video? Should I spend time just writing some important things, or just keep it? Or just you need some injection of Red Bull, or okay? Well, I will do it anyhow. I didn't get any answer. You are morning people, so there is a team of experts working constantly in every box. Okay, and so it's interdisciplinary. And you have geologist, okay, you have geophysicist, you have a reservoir engineer, you have an offshore engineer, you have an economist, okay, or an accountant. You can say just an accountant, an economist. We need to have a drilling engineer. Okay, and the production engineer, maybe, but okay. And this on top of all the others, like you have an HSE, you have a political advisor, etc. Okay, of all the parts that are a bit non-technical, but they have a big impact on the planning process. Okay, that we are not going to focus so much. So at the end, what do we evaluate? This is something very complex, and I can see that Milan, you're telling me, okay, they are interconnected. This uses to compute what, but what do I evaluate from this complex platform? What do I see? What at the end? What things do I pay attention to? So there are like three things. Okay. So the first indicator is economical. So this we are going to say that is evaluation criteria. The first and the most important, and the thing that if that is not good, nothing else is going to fly, is the economical part. And this is focusing on the cost, on the revenue, on the cash flow, and ultimately on the NPV. Okay, maybe the total project has a very high NPV, but I have to.
And yes. Then I think in the list of expertise, economist is more sound than accountant.
More?
I think economist.
Yeah,
is more sound than accountant.
Economist, usually the methods that they are using at the very early planning, they are very kind of cookbook methods. Okay, they don't use very sophisticated methods. So it's something that really an accountant can do. Okay, accountants. If you want to have some, for example, there are some more fancy variations in the hydrocarbon price. You want to include, and we will see now uncertainty in these parts. Then you need someone with more knowledge, like an economist. Okay, but if it's a cookbook, you follow. Then you can use just a person that has accounting education. Okay, and that is familiar also with the tax regime. Yep, but I will put here the word economist if you want. Sometimes you execute things a bit more complex. Yeah, so this is the main and the primary indicator. Okay, then the second. Okay, so I was saying that maybe you have a very nice NPV, but the cash flow initially you will have a very heavy expenditure. Yeah, you will need to get this money someplace. So that might be and you might get it from stakeholders. You might get it from loans. You might get it from partners. But that's something also some things that you have to. So the investment that you have to consider. Then we have the schedule, and the schedule here it refers to the project schedule, the timeline. Okay. Then the resources that I need inside the company. If I'm planning to develop in 6 years, for example, and I will need a lot of employees that I don't have, that's something that I have to take into account. And the project management in general. And then I have risk. Okay, what is the risk associated? So that's the evaluation criteria that I have, more or less, okay, very roughly. And also to note some things that we don't have. This is not, let's say, this is not a deterministic process. Okay, deterministic, you have one value, one input. Okay, you go, you have some function, or you have some process, or you have something that gives you an output. Okay, one single input, like an equation. You process it, gives you one output. When you have a probabilistic, okay, you don't have really an input. You're not exactly 100% sure about this value, about this input, but you have a range from minimum to maximum. Range of values for the input. Okay. So for example, if you say that we're talking about porosity, okay, we can say a minimum, average, okay, or base, and a low value. Okay, you have, it's a range at the end, but you have three distinct values. So one way that is deterministic, you go and just put the first value here, you compute all of that, you put the second value, and you put the third value, and you obtain a variation, for example, of the NPV. This is a deterministic analysis. Is it clear? Yeah? Okay. Then you have the probabilistic, that you still have a minimum and a low, but you assume that there is some values that are more likely than the others. Okay? So, do you know probability, where it is? How many of you have taken a statistics course? 1, 2, 3, 4, 5, 6. Okay. For case, what is probability? Is the chance, right? The chance of occurrence of an event. Yes? Okay. So in this case of the porosity, if we have the porosity, and we'll see just now an example, but if we have the minimum and maximum, if we say that they have equal probability, we don't distinct between them. It could be any place in between. So you say that all of them have the same probability. Okay? You can really take any value in between. So the probabilistic analysis is assuming not only that you have three, but you have a distribution, a probability density function. Okay? You have a distribution probability, so the probabilistic, that there is a probabilistic distribution for each input, okay? Or not all of them, but for the most relevant. And we will see later how then you say, okay, now it's not only a value, so really do I have to make calculations for each one of these values? How do I do it? Because now I don't have here just one porosity, but I have this distribution of porosity. So, and we will see later, I'm saying later, but we will see later how we do that, okay? So here we have, just to finish this part, this is not a deterministic process. So in deterministic, we have discrete outputs. These are calculated based on a minimum, a mean, and a max. Okay. And really we cannot guarantee that the mean case is the base case. Okay. We can say, okay, the worst case is if we take all the values to the minimum, the best case if we take all the values to the maximum, and the base case if we just take the middle. That's not like that, because you cannot guarantee that, for example, the minimum in porosity will be the maximum in water-oil contact, will be with the minimum in water-oil contact. You might have all kind of combinations. So that is not, you cannot do it in a deterministic approach. So that's this part, that it is very unlikely that the minimum will occur simultaneously for all variables. Okay? The minimum or the maximum. You usually have, some of them have mean, some of them have max, some of them have, so that's what I want to capture. While in the probabilistic, okay, then I have here the full range. My idea is to get the full range of possible outcomes. So I want to get my NPV, a similar graph, right? But I want to know which value is more likely to occur. Which value has the highest probability? I'm not interested now that this will give me just one NPV mean, NPV max, and NPV base, because I'm not sure really that this is a good indicator. I prefer to have this to see from all the possible outcomes of NPV, this is the most likely to happen, to base my decision on that. Okay? Yes. Okay, so I think we can, do you want to break? Yes? Okay, let's take a break, 15 minutes. Okay, one thing that this is usually called the value chain model. Okay, and again I did the same mistake. Didn't put enough space at the top. Okay, is the value chain model. And the other thing to comment was, oh yeah, okay. Okay, so there are several tools and we are going to go through some of them. There are and remember that also depending on the phase, you sometimes don't have just one architecture, but you might have 3 or you might have 4. You might have different options. So you have a value chain that has, in each box you have certain options, and then when you go down in the decision process, you just select one, and then that box will have only one. There are several tools to evaluate the project, and so you have probability plots, okay, like the one that I showed before, this one, a probability plot, time plot, You want to see what happens with the cash flow with time. You want to see when each phase, each event is going to happen in the field. Decision trees. When we have a very clear, or we have a decision that we want to go 3 options, there are some tools that are called decision trees. How many of you are familiar with decision trees? No? You are? Yes. Okay. Then we have tornado plots. We have also, in the same idea, it's called also spider plots. We have summary tables. Okay. With either one value or with advantages and disadvantages. And we have also qualitative ranking. When you have some things that have advantages and disadvantages, you try to assign a value to this property or to this characteristic, and then you sum how many points each alternative has. And that's a way to give some numerical value to something that is qualitative. So let's put that small comment here. Like if, for example, you have an FPSO and a platform, the FPSO has storability. So you assign, that's something that you want. So you assign a number instead of, for example, from 0 to 10, the FPSO will have 10 and the platform will have 0. Because it doesn't have any storability. So let's go a bit deeper into probability. And for that, before we go to the classical example, that is reserve estimation, let's take one example of a project that I worked with some years ago that is about, so let's take just before that, we are going to focus it on reserve estimation, and we are going to make a very simple example. Reserve estimation that has a probability distribution and Monte Carlo. Okay. We are going to start with an example in Excel. Okay. Yeah, here you had a nicer plot, but it has some things missing. So I decided to do it myself, but maybe I can paste it just in the notes so you have it. We can maybe put it after here. Okay. So the example is, I was involved in a project some time ago, and it's, the mud pump during the drilling process. You have to have, that you inside the string you circulate a substance called mud, right? Maybe too basic. Yes. What are the purposes of mud?
To get up chips and
To take out the cuttings. That's one. Second,
to cool the bit.
to lubricate the bit, to cool it, and the most important is pressure the barrier, okay, that avoids nothing comes into the wellbore. And I think there is something else. Cutting, lifting, lubricate, cooling.
Mud cake.
Hmm?
Mud
The mud
avoid
cake.
loss of method.
Yeah, but the mud cake is usually something we want to avoid. So it's not the main function of the mud. Yeah, maybe I'm missing something. Okay, but you have, you know, the story. You have mud, and you circulate through the system, and you have a pump that does this circulation. Yeah. So there were two pumps that were working in parallel. We can make a small drawing here. Okay. And they had different. First, they were a special type of pump. This is in Oseberg East. Okay, and the platform was very congested. So they went for a design that was the vendor promised that was very compact. Okay, and compact, I'm saying like almost like twice a man size, but it was very compact, and it looked like this. Okay, you know that usually pumps are triplex pumps. We will see just now, but that's how the pump. If you take out the cover and everything, and a man maybe was about this size. Okay, so it was 1.5 twice the size, and this particular pump had had 6 pistons. Okay, these pistons go up and down, like it shows in the figure, and they are driven by this motor rotates, and then this disc is just following the profile, going up and down, up and down. Is that clear? Yeah. So, and all of these cylinders, they drain from a common suction tank. So the ball allows, that's a valve. Okay, these two are valves. So they allow the flow to go inside the chamber, but when you go down, they don't allow it to go back. That clear? Yeah. Let me just put a figure. Is those of you that have some mechanical engineering background, that sounds very, very familiar. Okay. Okay. So when you go down, that valve, which is the suction valve, is closed, and this valve opens, and then you push the fluid to the discharge line. In this case, the discharge line was like a ring, where you had all of them were discharging and was collecting, and this was the pump discharge that you see here. And on the suction, when this goes up, this one closes, and then you suck. It's like you're allowing fluid to come outside to the chamber, right? So to make the story short, one of the pump had, so what was failing was the valve. Okay, these valves that are here that look something like that. Okay, and if we have a more schematic drawing, it will look something like this. Okay, where the fluid goes inside this area and pushes the valve open, flows around, and then when the piston goes down, for example, it will close. And they were having, one of the pumps was having much more failure of these valves than the other. So we had the theory that was because the speed of the pump first, usually the triplex pumps that are the ones used, triplex pumps, they have almost the same arrangement, pistons going up and down, but they are simpler. They have a common suction manifold. Then you have this arrangement. And you have a common that's how the piston looks like. And the piston has a speed of rotational speed of around maximum 120 RPM. Okay? While this pump had all the way to 200 RPM. So our assumption was that the pumps were rotating much higher speed, and that caused a high valve failure. Okay? High pump speed and then you get high valve failure. Okay. So we ask for the speed of pump that is called SPM of pump 1 versus time. Okay, and it does something like this, okay, changing during a drilling operation. And then we ask also for pump 2. SPM stands for strokes per minute. Okay. Stroke is when the piston goes up and down. So if you put the two of them, there might be not so obvious that they are working, one is working quicker than the other. If you look, just overlap these two drawings. Okay. Might see, okay, this one was going faster this period, but then this one was going faster. So how do I really calculate or determine if one pump was going faster than the other? So for that we are going to make a probability analysis of the data, a frequency analysis of the data, to see which velocities are the most frequent. Okay. Yes. So for that I have uploaded also, if you want to do it together with me here in class, I have put part of the data, anonymized of course. Okay. So here you go to classes, to its learning, you go to the day of today, and that's the Excel file. Okay. And I have just put, I think it's maybe 3 days, and they are the measures. So we took, that's the mod logging data. Okay. Every 10 seconds for, I think it's, let's open it to see how it looks like. So I'm going to use Excel for this exercise. Okay. Okay, so the data was gathered from the 7th of, until the 7th of May, and from the 1st of May. So it's 6 days, roughly. Okay, and you have, for each this period, these 10 seconds, you have the speed of pump 1 and the speed of pump 2. Okay, so let's put the units first. So here we put, this is in SPM. And this is also in SPM. Okay, and you have, and I will not plot it here because there are too many. Okay, so it will take maybe a lot of time to plot. 58,000. This is just a fraction. We were analyzing for the whole month, so maybe it was more than 1 million columns. Okay, and one of them were every 5 seconds. So let's try to make now the probability a plot. Okay, that we want to say, for example, here in the x-axis, that's usually how we make a probability plot. We have the speed of pump, okay, and here we have the frequency or the probability of occurrence. During that period. And we want to have here the minimum and the maximum, and we want to know which one of them occur most. Okay, is it something like that, or it might be something like this, or it might be something like this? We don't know. That's what we want to find out. Okay, but we already have data, so we can analyze the data and try to generate this plot. Yep. Has any of you done this before? A frequency plot? Not even in your statistics course? You have done it, okay. So you're going to help me if I make any mistake, okay? You're the one in charge of quality control. Yeah? You say, oh no, why did I say something? Okay, so let's first, we want to find the range, okay, the variation. I told you it was all the way to 200 and from 0, but let's just, we verify. We're engineers, we just don't, okay, you don't believe me completely. Okay, you want to make some quality control. So let's say minimum, okay, to calculate the minimum speed, okay, and maximum speed. We want to find the range that we're going to put in our axis. Okay, for that we just used a command. Okay, Excel, I just used the command min. Okay, I can even find it here. Okay, and I say min, enter. Okay, and it says returns the smallest number in a set of values. It's going to go through all the set that I give it like an input and tell me which is the minimum. Just all of you are familiar with Excel, yes? So I shouldn't go so for dummies in this part. Yeah. Okay. Okay. So I select min. I will select the both because my interest is to plot all the values in one plot. Okay, for both, and then see if one goes quicker than the other. To select the range, there is a trick. You can okay, you can select these two, for example. Then you use Control Shift down. Okay, I'm not sure if you knew that trick. Okay, but it's useful. Control Shift down. You can do it sequentially. And here I do the same for max. I want to find the maximum value, and of the two again. Okay, and it's really, I don't have to be dragging it with the mouse, and that's really a big saving. Okay. And here, surprisingly, the pump was not running at full speed, was running at 170, which is good that you didn't believe me. Okay. So now we say we want to have the SPM, pump speed, and I'm going to make subdivisions in speed. Okay, I'm going to say I'm going to subdivide that range in some particular values, and let's use maybe 10. Okay, so let's use 0, 10, 20, all the way to 170. And then what I want to make is to count how many zeros are in this for pump 1 in this column, and how many 10s are in pump 1, how many 20s are in pump 1, yeah. And for what happens, for example, if it finds 5 or 4, where is it going to put it? Okay, we're going to send a robot, Excel. Okay, it's kind of a machine that is very good at doing things that are repetition, that are just mechanical. Okay, so it's going to go C90. Okay, I'm going to put 90 here. Okay, count 1. Another one, I will count 2. Another one, I will count 3. But what happens if it encounters 92, for example? Anybody knows? No? So what it creates is a range. Okay, these values really doesn't represent exactly the value, but it represents a range. If I say 0, 10, 20, 30, okay, 0 really is between 5 and -5. 10 is really between 5.1 or, okay, this is usually the lower is in this range, lower, and this is less equal. And then this goes all the way to 14.999. Yes? And then 20 goes from 15 to 24.999. Okay? So every value that is in this range is going to be grouped under 20. That clear? Yeah? That's something important, and that's something that could make some change. If you use too wide jumps, for example, every 20 or every 30, you will see that your distribution looks very different. Okay, so the grouping is important. Okay, so you say here, let's put number of occurrences, and we have to make it for, okay, we have to make it for we have to have one for pump 1 and pump 2, right? Okay, to do that, to count, I have to select first all the cells that where I want, because it's kind of matricial function. Okay, it's not a function that I apply only on one cell, but it's a function that gives output a bunch of cells. It gives like a vector. Okay, so that's why I have to apply it on a vector to get a vector. Okay, so the function is called frequency. Okay. So I select the data array of pump 1. Again, this trick of Control Shift down is very useful. No, I don't close yet, comma, and then I want to give the bins array, and the bins are exactly, okay, this is all the data, and how do I classify? Give me the how to say, the reference against which count it, against which I should count it. So this is this column, and then to apply the function I have to put, I forgot, it's Alt Shift Enter, I think. No. Yeah, it's Control Shift Enter to apply the function. Instead of just pressing Enter, you have to put Control Shift Enter. Okay, too many tricks in Excel. Okay, and it did the counting. So let's just put here the tricks so you have them, so that we can maybe close or minimize. To send the selection tricks in Excel. Okay, Control Shift down. Or if you want to apply a matricial function, and this is a function that takes a vector and returns a vector or a matrix, okay? A vector. So instead of pressing enter, press Control plus Shift plus enter sequentially. Okay, very important trick and useful also for if you want to use any of these functions. So it tells me that I have, so if you see here already, most of the time or most of the occurrences the pump was operating at 0. Okay, so it was shut down. But if you see here, the next most frequent occurrence is when it was operating at 110. Okay, so that's the value maybe we want to compare with the other pump. What is the maximum that is not 0? Okay, just another quality control that is important. You say here sum, and you want to sum how many occurrences you had, and that should be equal to the number of data points in this column. Okay, the number of data points here is 58320, and here I have 58320. That means that all of these values, it assigned them to some value here, or to some VIN value. Okay. Now to make it more, you know, not having the number of points, but put it more general, we usually use frequency, relative frequency. Okay. In percentage, and here the relative frequency, and this is for pump A, pump 1. Okay, you could put it also, there is a way to put it down, and that's, anybody knows? Alt enter, I think. Yep. Alt enter, and then you send it to the second line. Alt enter. And here I'm going to divide this value times 100 divided by the total number to see how much of the time it was operating at 0, how much of the time it was operating at 10. And this number, if I drag it down, what will happen with Excel, it will take this cell, this cell, this cell, and this cell. And here, if I don't do anything, it will take this cell, this cell, this cell, and this cell. And that's something that I don't want. I want the cell, the denominator, to be all the time fixed. To do that, I block my cell and I put F4. Okay. 35% of the time in 36. Okay, and then I pull it down. 0, 20, 12, etc. Okay. I do the same very quickly for pump 2. And this should sum 100, right? Like a quality control. Okay, 100. Now I say number of occurrences. This is for pump 2. I guess that looks like you're not working with me, so I have to hurry and not keep you waiting. Okay, and here I have to again remember to apply it on the whole range equal to frequency. And here I have to say select this and comma, and here I have to select the beans array, and then to apply it, Control Shift Enter. Then the relative frequency is, I can just copy and paste from here, right? This number divided by the total number, which is the same for both columns, times 100. And now let's plot it and see what do we get. So to plot, I say insert chart, and we want to use a chart which is a bar chart. So let's some bunch of things came here, and usually what I use is a bar chart. So we're going to move it first to a new sheet, and we call it frequency distribution. Okay, then select, and that's going to be pump 1. The values in X are the speeds. The values in Y are the relative. Okay. And I don't really like this chart, so let's change it just now. This is pump 2, and X will be exactly the same, and Y will be this here. And we're going to change the chart type, and I want to go to a bar type or column. Maybe we can just put 1. Okay, sorry, let's just put pump 1. Okay, and now some rules. You're going to deliver graphs, okay, during your homework. So I want to be big enough, so usually with 18 should be big, then you put it in bold. Then please provide the axis titles. What is it? So here we say relative frequency of pump speed, and that's in percentage. And here we have pump speed in SPM. Okay. And also to add on the axis, you want to add the tick marks. the major outside, so it will show you exactly where the number is located, also here. Outside. And you want also to use a black line, because when you print it, this gray is not very good. Okay, and finally, what we are going to make is, I don't want to have any width. Okay, I just want to have that all of them will be close to each other, because really there is no value in between. It just goes from 100 to 110. And then I change one last thing, I put a solid line. Okay, so that's my frequency diagram of the operating speed of pump 1 during that period. A big part of the time was just idle, was not doing anything, but then a big part, we can say it was mainly around 110. Okay, so let's repeat the same. So here I change the name. Okay, create for pump 2, and here I want to change, so this is pump 2, and here I want to change the data, and the name will be pump 2, and it will be these values here. Okay. Okay, and you see this pump, it's operating around 120 most of the time, so it's a bit higher. But this is, I think, because we just took 6 days. If we took the whole month, this pump 2 was operating at much higher speed, was actually around 140, and was a very clear peak. Okay, we are taking less time, so it might be slightly different. So let's take that. Wait, we're about to finish. Okay, so if you put one on top of the other, that's maybe a homework, you will see something like that, going up 120 and then going down. Okay. While this one is something like this. Okay, so in average, pump 2 was running at much higher speed than pump 1. Okay. Now this is relative frequency plot. Or we can also call it probability, okay? And it's called probability density function. And why do we use the word probability? Because it's for things that not only we are going to assume that not only this is something for a fixed period, right? But there are some things that we will say they always behave like that. It's like porosity. Okay, porosity, you make your analysis and it's not going to change. It's all the time going to exhibit the same distribution for that particular field. Okay, so in that case we call it PDF of the function, and it might be based on data, it might be based on, because you know that porosity all the time exhibits certain particular distribution. Okay. Let's, before we finish, to talk about the cumulative probability. That this is a bit tricky, but this is actually what we are going to use for the reserves, probability. Okay. And the cumulative probability is nothing more than, we are going to add one more line here. We're going to say cumulative and this is in percentage, and we are going to sum the probability up to that value, of occurrence up to that value. So here we're going to sum what we had before plus the current probability of that particular number, and we drag it down and it should give all the way to 100. Okay, so we plot it again. Let's say copy, okay, and we change it to cumulative. This is for pump 1, right? Don't worry, we're about to finish. Don't despair. Okay, the data we want now, it's on the Y, it's this. Okay, and okay, and it should go all the way to 100. Okay, actually we don't plot it with these blocks, but we plot it with this line, this line. Okay. And sorry, I have to change this. It's okay, so what does it mean? Okay, this chart, why do we do it? Why does it matter? Okay, what does this indicate? For example, 40 is the pen. Okay, for example, 60, that 60 has a 40% cumulative probability. What does it mean? Okay, that there is a 40% chance or 40% probability that this number that you will be operating at 60 SPM or below, right? Yes? Understandable? Yeah, okay. So we follow the same logic. For 120, there is 80% probability that all the values will be operating at or below 120. And subsequently, as the maximum was 170, all values, 100% probability that we will be operating less than 170. Okay? Now you see the usefulness of that, because if we now plot reserves here, we want to know there is 80% chance that my reserves will be at least this value. There is 10% that my reserves will be at least this value or less, right? You see a bit the importance of this plot. Yes? Okay. And also this is a discrete, okay? We have work here, we have worked so far with a discrete distribution, Okay, and discrete because we have values. Okay, we have something that we measure and we generate from here, we generate the values. So that's why we obtain a discrete. But we also could have, it is possible. So if you want to have porosity, for example, if you, let's say that you make many samples, okay, of porosity of your formation, you drill 100 exploration wells, for example, okay, which might not be, or you in the same well take 100 samples. If you put all the samples, you can do exactly the same. The distribution of porosity, it's something like that, for example. PDF of porosity looks like that, and the cumulative of porosity looks like that, right? If you had the samples. But as you have limited information, you rely, it's possible to use continuous models, okay, or using continuous distributions, using analytical equations. Okay, and here I'm going to pull just two for you can see as an example, and very simple to use. And we are just about to leave, so just allow me 2 more minutes and don't escape. Do you have any other class after this? Okay, so we have, this is the Gaussian distribution, Gaussian, and this is the Rayleigh distribution, okay? And this is the PDF, okay, the probability of this parameter, that this is like an X, okay? Can be anything, can be porosity, can be pump frequency, can be permeability, can be everything, okay? And that gives you, the Gaussian gives you something that is centered, is typical what you use, what you suffer during your evaluation. Okay, professor says I always want to have a Gaussian distribution. Okay, so that's why you suffer. This Gaussian guy, you should really find a way to travel in time and do something. Okay, and the Rayleigh is something that is shifted. Okay, yeah, and we can tune. It is possible with discrete data to tune to a analytical probability expression. Okay, and that maybe you will find out next for the exercise. Okay, but it's possible if you have data, if you have the points, you can tune and find this expression. Really remember what you need is, in this case, is just, this is the standard deviation. Okay, this in this case is x, okay, the variable. Okay, and you can tune it, and then you use that distribution. Okay, and most of the knowledge, just the expert comes if you have a few measurements of the porosity range, of the permeability range, how to propose a realistic distribution. That's the expert, okay? The expert knows in the area, more or less, we have this distribution, that distribution. If you don't have no information, you just assume a uniform distribution. I really don't know anything about the area. So I think we should consider that everything has the same probability. Okay? Understood? Any question? No? Okay, to summarize, today we did cover some things that we didn't cover last class. Production plateau, height and length. We covered also the value chain that we analyze when we are in the project planning. And we went a bit into the probability and why is it useful for quantifying the spread or the change in one variable. Next class, we're going to use it for reserve estimation, a very simple example. And I see if we have time for more than that. Okay, we're going to talk about Monte Carlo also. How do we propagate the effect of the uncertainty? How do we calculate this distribution but for NPV, for example? Yep. Okay, see you on Thursday.